So now we know that when the two lines are meeting, so temperature and dew point temperature are touching each other, it means that the relative humidity becomes 100%, so the air is saturated, and that's where the cloud is. There is a specific type of cloud that you still need to recognize, and there is an example of that here. When we are zooming in, we can see these features a little bit better. So here the dew point temperature and the temperature of the environment are the same at the ground level. So the cloud is basically on the ground, and this is something that we call fog. Fog is usually in a very shallow layer, so it's not a deep cloud, but it's anyway a cloud, and fog is significantly affecting visibility, for example. Here you can also see that the zero isotherm is here, and the environmental temperature and the dew point temperature are on the positive side of that. It means that this fog is consisting of liquid water droplets, and that the 2 meter temperature is larger than 0. But there is also a possibility to a fog like this. Now you can see that it's even shallower layer where the fog is, so these lines are meeting only at the ground. But now the temperature is negative, so this is something that we call freezing fog. And freezing fog is building rime on top of some surfaces. And also there is a case where there is almost a fog, like in this example. So there is a very thick layer of cloud at the lower levels, but the lines are not touching each other exactly at the ground. So here it's not fog, because they should be touching each other for the relative humidity to be 100%, but they are just barely separated. But still, this is something we call stratus cloud. So under the stratus cloud, the visibility might be okay, but if you have some tall buildings, chimneys and so on, they seem like they are kind of cut off because they are inside the stratus cloud. Low-level clouds and fog is extremely important in aviation, so remember to pay attention to those. And sometimes models are not very good representing fog or forecasting fog, so you have to always consider possible errors when trying to forecast fog. The next thing that we are gonna learn to interpret from the sounding is precipitation form. When we are trying to forecast precipitation form, there is a definition in meteorology that we're going to use, and it's called wet bulb temperature. So instead of using just the normal temperature and dew point as such, we're actually using the definition of wet bulb temperature when we are trying to consider whether the precipitation form is going to be snow or rain or sleet. And the ideology in wet bulb temperature is that you are evaporating moisture into a layer of air. And when you are evaporating something, this layer is going to be cooling down. On the other hand, when you are evaporating water into that layer, it's also getting moisture. And maybe the quickest visual way to see that is only to use this kind of approach, where you note your temperature from the sounding and also your dew point temperature, and you bring them together. So if your temperature is +3 and your dew point temperature is -3, your wet bulb temperature is close to 0. So you're just gonna be bringing these lines together to meet in the middle. And if the middle point value is positive, it means that the potential precipitation form is probably rain, so liquid. And if it's negative, then it means that it's probably snow. And if it's very close to 0, it might be sleet. Of course, this works maybe in the 95% of the cases when you are considering these 3 precipitation forms. But extremely intensive rain can also play a contributing factor to the precipitation form, and that this method is not taking into account. But usually this works just fine. So for example, in this sounding, my temperature is actually close to 3 degrees Celsius and my dew point temperature is minus 4.5. So it means that my wet bulb temperature is very close to zero, so it's probably gonna be sleet. Let's take another point. For example, here, also the model is predicting some precipitation here, and I can see that my dew point temperature on the left is very close to zero, and my 2-meter temperature, or the 10-meter temperature represented in the sounding, is clearly positive. So when you are bringing these two values together, the most probable precipitation form is rain, because it's on the positive side of the zero isotherm. And then there are some extremely easy cases, like if we take a sounding inside this precipitation area, I'm gonna be seeing that all of the sounding is on the negative side of this zero isotherm. So the precipitation form is no. Here, on the other hand, there is precipitation in the forecast, and you can also see this very thick cloud, and it's on the positive side of the zero isotherm, so this is gonna be rain. The trickiest ones are always when your dew point is negative and your temperature, 2-meter temperature or 10-meter temperature, is positive. Then you have to consider whether it's gonna be rain or sleet or snow, and very small changes or errors in the models can lead to a wrong precipitation form forecast. These precipitation forms can also be forecasted by the models. So here, for example, I have precipitation form forecast from 3 different models. But don't trust them blindly. You should always double check what the model is forecasting using your sounding tool. So here I have an example sounding of the situation where the model is predicting freezing drizzle. So freezing drizzle happens when you have a drizzle cloud. Drizzle cloud is usually very close to surface, and it should be at least 1 kilometer deep in order to produce precipitation to the ground. And it becomes freezing when the cloud is on the negative side of the zero isotherm. So the water droplets are not yet freezing, even though it's on the freezing side of the zero isotherm. But when the precipitation falls down and these raindrops or drizzle drops are hitting a surface, they freeze immediately. And that's why it's very important to be able to forecast these situations. And when your cloud is situated between 0 and minus 10 degrees Celsius, that you can consider to be potential for freezing drizzle. And here is an example. This could very well be freezing drizzle cloud. So at this time, I could trust the model. But also note that when the cloud becomes deep enough, it tends to have also other precipitation particles inside. And especially if the top of the cloud is getting colder than the minus 10, it might be that there are snowflakes that could be then collecting these freezing raindrops from the cloud when they are coming to the surface. And that's when you get those very rimed snowflakes. That's always a sign of having super cooled water present. So maybe here, even though the model is saying that it's gonna be freezing drizzle, I would say that this is probably gonna be already snow because the cloud is pretty deep. It's almost 1.5 kilometers deep. And it's just after the snowfall, so I might consider different precipitation form here. And here is another example. Here at the top of the cloud is getting colder than a minus 10 degrees Celsius, so judging by this sounding, I would probably say that the precipitation falling to the ground is no. Then there is one more precipitation form of which we can find an example. Here we have snowflakes falling to this layer of warmer air. So we have snow and it becomes here. Zero isotherm is here. So the snowflakes falling to this layer would start to melt. And then they continue their journey to the ground, where the temperature is freezing again. So these melted or almost melted snowflakes hits the surface, any surface, it will freeze immediately. And this sounding is typical for something we call freezing rain. And usually freezing rain cases are very bad because they have a lot of consequences, aviation as well as to the traffic overall. But if the layer of the colder air near the surface is thick enough for these melted snowflakes to freeze again, you might get something we call ice pellets. So these rain droplets actually have enough time to freeze again, so you would get these quite clear little ice balls. And if it's the freezing drizzle that has enough time to freeze, that precipitation form you would call snow grain. And these snow grains appears a little bit different from ice pellets because the snow grains are opaque, so not clear. Then another thing you can actually see from the sounding is advection of warm or cold air. And you can actually see that the precipitation form is gonna be snow. But what I want you to pay attention to now is the wind barbs on the left. So here you can see that at the surface the wind is easterly, so it's coming from east. But then along the height it's actually turning to be southerly. So our wind is turning from east to south when we are going higher up in the atmosphere. So it's turning clockwise, and when our wind turns clockwise, we say that the wind is veering. And when the wind is veering, it's always a sign of warm air advection. So this is actually a frontal cloud that we're having here, and based on this knowledge that we have now, so we have veering winds, warm air advection, it's definitely a warm front that we tend to have quite a lot at mid-latitudes. So when the front is passing, we can also expect to see some cold air advection. So I found a point here. You can see that at the ground we have northwesterly flow, and then along the height it's gonna be turning to westerly. Now the winds are turning anti-clockwise when going higher up in the atmosphere, so this is cold air advection. And the advection happens in this layer where the wind direction is changing. So remember to consider this as well when you are wondering what happens to the temperature or the dew point in some layer. So now that we see that we have cold air advection, I can actually go forward in time and animate. But because of the cold air advection, I would expect this layer here, so from ground to the 3 kilometers, be getting colder. So I'm expecting this layer to get colder. Now I'm going 6 hours forward and see what happens. So already this layer became colder, so if I go back, I can see that I don't have this warm notch anymore. In extremely cold temperatures, there is one thing you might want to consider as well. So I took a sounding from the Lapland, and this is midwinter time in Finland this time of year. So you can see this layer here. You can see how rapidly and in a very shallow layer this air temperature and the dew point are dropping. So this is something that we call low-level inversion, and this is something you need to consider, especially if you happen to have continental climate. When you have this kind of situations, it means that your air quality might be actually getting poorer, and the reason why your air quality might be getting worse is that this layer is extremely stable. Air parcel cannot penetrate through this, so you would need to have sunshine or higher wind speeds that could break this inversion layer. So all the smoke or the fumes from the cars, they are kind of trapped inside this inversion bubble that sits on the ground. And also remember that when you have these inversion cases, the models are not good at trying to forecast the temperatures in these situations. So here I'm using our high resolution model MEPS. That is okay, trying to represent these situations. But usually you can still decrease this temperature by 5 to even 10 degrees Celsius before you actually reach the observed value. And if I'm using ECMWF model sounding to the same place, now it's in blue color, you can see that because of the resolution, it's not even that good of trying to represent the strength of this stable inversion layer near the ground. So if I would be forecasting temperature to this point, I would say the temperature would be between minus 20 to minus maybe 25 or even 30. And the last thing that you can see from the soundings, especially during the colder times of the year, is the potential for snow melting, so whether it's happening or not. And here is actually a great example of that. So my temperature is over 10 degrees Celsius, and I don't have any clouds here. You can see that it's clear sounding. But my dew point temperature is on the negative side. So actually, this layer of air is extremely dry. So sure, the snow can evaporate, but that's usually not what's happening. Usually it's melting because of the warmer and moister air. That's the most effective way to melt the snow. So I would like to see my dew point temperature on the warmer side of the zero isotherm in order to see some quicker results in the snow melt. And this is something that occurs quite a lot, especially in Finland during the springtime, that our temperatures could be even plus 7 degrees Celsius, but our dew point temperature is very cold. So the air is super dry. And that's why our wet bulb temperature would be just barely on the negative side of the zero isotherm, so we can actually have snowfall even though when the temperature is plus 7 degrees Celsius. So that's one more reason why you shouldn't blindly trust your temperature value when you are considering precipitation form. You have to consider this moisture content as well.